Welcome, everyone. This is the MAREA, the Mid-Atlantic Renewable Energy Association. MAREA is a nonprofit dedicated to education on renewable energy and sustainable living issues. Our speakers are leaders in their fields, and this year they ranged from solar energy storage to Atlantic wind farms and native plants in your backyard. Tonight we'll learn about the future of geothermal energy. And coming up on October 26th, we have open mic night, which will feature a panel of officials from several colleges and universities. And these officials are responsible for leading the sustainability initiatives of each of their respective colleges and universities. So it should be very interesting. And again, that's October 26th. After that, we'll take a 2-month break when we'll start again in January with our speakers again for next year. Preliminary, I would say we have some very interesting topics slated for next year, and we hope to give you more on that at our next meeting. With that, Chuck, you want to take it away and introduce our guest?
Sure. It's really my pleasure tonight to introduce Dr. Tester, who is a professor of sustainable energy systems at the School of Chemical and Biomolecular Engineering at Cornell University, and Cornell's principal scientist for the Earth Source Heat Project, which you'll be hearing about tonight. He is a founder and served as a director of the Cornell Energy Institute for a period of almost 10 years and is a fellow in the Atkinson Center for Sustainable Futures and a Kroll Energy Fellow. Prior to his appointment at Cornell in 2009, Dr. Tester was a professor in the Chemical Engineering Department at Massachusetts Institute of Technology and served as the director of MIT's Energy Laboratory for 12 years. While at MIT, he had the privilege of chairing an 18-member international panel that evaluated the long-term geothermal potential within the United States, resulting in a major report, The Future of Geothermal Energy. Dr. Tester was the U.S. representative for geothermal energy to the IPCC working group, which evaluated the global potential of renewable energy. In 2011, he received the Special Achievement Award from the Geothermal Resources Council. He has published extensively in the field of energy, having co-authored over 300 research papers and 13 books, including a textbook that I actually used in my course about choosing among the options in sustainable energy. It's my true privilege to bring Dr. Tester to the MAREA crew this evening. He is leading Cornell's decarbonization efforts to use geothermal heat extracted from rocks at depths of 3 or more kilometers for supplying the campus district heating systems. So slip back and listen and learn about digging more deeply into geothermal for a more renewable future. Dr. Tester, the floor is yours, and thank you so much for sharing your time with us.
Well, thank you. Thank you for that. That was far too magnanimous an introduction, but you'll see as we go through this, it's not just about me. There's lots of people involved with this project, and I couldn't do it without them. Okay, so, and I've got a pointer on here. Everyone can see that all right? Okay, so I'm going to keep moving along here. I hear a little echo. Is that because there are other people with speakers on or whatever? Are we good? Good to go? Okay. Okay, so I'm going to give you kind of a brief outline of what I'm going to talk about. And I'm hoping that I'll cover things that some of which you may know a little bit about. Hopefully you'll get a little deeper understanding of geothermal, but this is sort of a geothermal energy 101 for a few slides. And then I'm going to try to cover throughout periods of this talk why this is a rationale, not just to be applied for district heating at Cornell, but also in New York State more broadly, and perhaps certainly Pennsylvania, the northern states in the country, certainly the Appalachian Basin for that matter, and could have a large impact on the U.S., particularly if we're interested in decarbonizing the way in which we provide energy. And then I'll talk more specifically about Cornell and how we're trying to do a full integration, a systems approach, if you will, to integrating what we call earth source heat, our sort of version of geothermal. In this particular case, to provide baseload heating with waste biomass peak heating, and also other aspects of renewable energy that could be provided, particularly by solar, wind, and hydro, because the idea is to decarbonize the entire campus in roughly another 13 or 14 more years. This has obviously been a multi-phase kind of approach, and Cornell is in the first phase of this in the field work, which we call the Cornell University Borehole Observatory. This is an exploration well. It represents what we refer to generically as kind of a living laboratory to look at the subsurface that we're going to have to deal with as a way of extracting thermal energy from the earth and tying it to Cornell's district heating system. So there are a lot of people involved with this project, and I just want to be clear that it's not just about a single thing. Many faculty involved in broad different distributions, some in earth sciences, some in more conventional engineering, some in economics. The facilities group itself is pretty enlightened at Cornell, and there are two particular engineers that are heavily involved in the work we're doing. Steve Byers and Ole Gustafson. And there are a wide range of students, postdocs at all levels, and even a number of undergraduates who've been involved with the program for years. So it involves facilities engineering, civil and environmental engineering, chemical engineering, now also material science, as well as earth and atmospheric sciences. And so if we look at this and sort of a quick picture, you can kind of divide up the utilization into three bins. One is electricity. That's sort of the largest single part of geothermal story in the United States right now. We're the world's largest producer of geothermal electricity. Unfortunately, none of it's in the East. It's all isolated in a few states in Western US. The other aspect that you're probably familiar is number 3 here, which is geothermal heat pumps, where we use a shallow ground connection as either a source or sink at moderate temperatures for heating and cooling applications, particularly in individual buildings, sometimes clusters of buildings. But the part that I'm going to talk about tonight to bring you to a new maybe understanding of why this could play a bigger role is the direct use of the thermal energy itself. Heat pumps are good, but they require electricity. If we go to direct use, we would be using much less electricity and much more the actual thermal content of the fluid that we're taking out of the ground in, say, a district heating system. So when you deal with any kind of geothermal system, whether it's a classic natural system, so-called hydrothermal reservoir, or whether it's an artificial system where you're creating certain aspects, you have to have certain characteristics to make it work. The first is it has to be hot enough, and that hotness in terms of the rock temperature has to be accessible. So it has to be reachable by conventional drilling, and not too deep because it becomes very expensive, but yet deep enough so that it contains the right temperatures that you're interested in. So not at the shallow surface. We're unlikely to have that in this part of the US. So we're going to have to be in a range of depths that are of the order of, let's say, 10,000 feet, maybe a little less, a little more, a few kilometers or so into the Earth's crust. The other thing is you have to usually have a connected well system where you're injecting water into the reservoir in one area and recovering it in another. And it has to circulate over a large mass of rock so that it can be continually reheated. Cold water being injected at one end of the reservoir, hot water being extracted from the other. And that water has to be produced at a high enough rate to justify the kind of large capital investment you're going to have to make in this kind of system. And it has to last long enough as well. So the lifetime of a given reservoir as well as the production capacity is quite important. And those are the two big critical metrics in any kind of economic analysis. And then ultimately, you got to figure out how you're going to use it. And I pointed to the two areas, electricity and direct use. Heat pumps is a third, but between direct use and thermal use of the thermal energy to produce electricity, these are the common modes. These are a couple of examples of U.S. plants right now. This is one out in California near about 90 miles or so north of San Francisco. And it represents a large resource that consists of many modular plants. At one time was producing almost 3,000 megawatts of electricity. Now it's much less than that. There are reasons for that we can get into in the question period. But I want you to migrate away from that and to think about geothermal more broadly now, particularly in the sense of something that could be reviewed as a range of different types and grades within what we'll call the continuum of geothermal. And this represents characteristics that involve temperature, and usually we express this in terms of how fast temperature rises as we drill in the earth. So that's this scale over here. This is degrees centigrade per kilometer of depth. And the other characteristics is how much fluid might we have present, either naturally or fluid we have to put into the system. And then what is the natural connectivity, usually expressed through terms such as permeability and the like. So what I've done is taken a few liberties here to scale this back to a two-dimensional graph. Up here in the left-hand corner, we have very low-grade systems. Unfortunately, this is what we have in the region we live in right now. And down in the right-hand corner, we have extremely high-grade systems, what we might find in the American West and some other countries that have very high-grade systems. So they would have low gradients up here, high gradients down here, would have large amounts of natural fluid present and very high permeability. Whereas we could be anywhere in this continuum with respect to gradient, fluid content, and permeability and still have a good geothermal resource. And it becomes the idea of an engineered system that we try and make this work. Let's see if we can move this along. So remember the three critical ingredients: temperature, reasonable depth, sufficient permeability or connectivity as we're referring to it, and sufficient hot water or steam. So if we look at the United States and try to come up with a way of kind of representing, I'm trying to get rid of this thing and I don't know how to do this, but it's a kind of, it's interfering with my screen, not your screen. So I have to move this around a little bit. So bear with me. So this is a map which shows a representation of what the Earth might look like in terms of temperatures at a pretty deep horizon, to 5.5 kilometers, over 15,000 feet deep. And you can see some features on it right away. The hotter temperatures appear in this redder region are obviously localized over in the western part of the U.S. and somewhat colder temperatures, quite a bit colder in the eastern side. And you can see anomalies here. This happens to be Yellowstone out here that I'm pointing to. We're not talking about going to Yellowstone to develop it, but it gives you an idea how large the thermal anomaly is at Yellowstone. It's a protected area, clearly in a national park. But this feature over here, which represents really the Appalachian Basin, also is rather interesting because it's not as low grade as the surrounding strata and rocks. It has higher gradients, it has higher heat flow, and it covers a wide range of Pennsylvania, certainly New York, and certainly West Virginia, where at those depths you would reach extremely high temperatures, certainly high enough even to generate perhaps electricity, but certainly far in excess of what you'd need for heating. For instance, if we just look at this color in here, this is a range of about 150 centigrade, far above what you'd need for a district heating system. But when we start to look at the economics of this in the context of the resource itself and where the resource is located, it immediately leads you to consider district heating and cogeneration in the eastern U.S. And there's a simple engineering reason for this. When we take fluid out of the ground that's hot and try and convert it into electricity, there's an inherent inefficiency to that. And the efficiency goes down as the temperature goes down of how much of that thermal energy we convert into electricity. Typically, geothermal power plants are about 10% efficient on the thermal side. If we had lower temperatures, that would be even lower. So it makes a lot more sense to use that subsurface environment to provide heat directly, where you could essentially use all of the heat without having to try to convert a portion of it into electricity. Okay, I'm having trouble on changing the slides for some reason. I don't know why. There we go. Okay, so the concept, if you don't have a natural system, is you go to what's often referred to as enhanced or geothermal energy system concepts, where you would provide some of the ingredients that nature has not. Namely, you still would drill wells. They have to be hot enough, so that part has to be given to you by the natural environment. But it might not have the permeability and might not have the natural fluids in place. So you would create a system that would consist of either taking advantage of natural fractures that are there, which are pretty common in these systems, and injecting water on one side and producing it on the other, sweeping it across large volumes of rock. And so that's the concept of a sort of enhanced geothermal system. And boy, this is really going to slow me down here because it doesn't seem to want to work. Okay, so if we look at EGS as being broadly defined as engineered reservoirs that have been stimulated to emulate the production properties of high-grade commercial systems, high-grade hydrothermal resources, as they're called. We know a lot about those already. They're in existence in many countries, including our own, so we know what those production properties have to be commercially viable. And okay, and another aspect of this is, what does the resources look like as we go across the country? This is some stuff that came out of that future geothermal thing. And one of the things, the questions that people often ask is, how much energy do we really have in place? Well, it turns out there's a huge amount of crustal energy that's accessible to us. This is the thermal energy scale here in big units. These are exajoules. To put it in context, we use about 100 exajoules per annum of all the primary energy we consume in the United States. So 100 exajoules are annual consumption. These represent different categories: low-grade EGS on the left-hand side, mid-grade here shown more in the middle. These are two different types of natural systems, the high-grade geothermal. Regardless of how we look at this graph, we're not going to run out of geothermal heat that's in the ground. The real trick is figuring out how to use it and use it economically. So the high-grade systems aren't always going to be in the right place where we need them. These geopressured systems are primarily in the Gulf Coast area, but this low and mid-grade EGS, as it's called here, is all over the place. So effectively, it gives us the ability to look at geothermal as a U.S. resource rather than just as a Western U.S. resource. And so to make it work, and this gets a little technical for a while, but just bear with me. Remember that graph where we showed connectivity. So that's what we're trying to make sure, that we have sufficient connectivity in these systems. And frequently this is represented, and there should be a graph coming up here. There we go. This is a picture that kind of gives a three-dimensional view of what a reservoir might look like. And the colored regions represent areas that have shown where fluid is being injected and where it induces very low levels of microseismicity, where we can actually map where the signals are coming from. So it gives us a sense of the physical scale of the reservoir. And you can see that it has dimensions of the order of a kilometer or so. So if we were to rotate that, it would be about a cubic kilometer. And it turns out a simple calculation will show you that to meet that criteria of sustained production, we need to have effective volumes of about a cubic kilometer for 2 wells. And we need to have heat transfer areas that are of the order of 1 million square meters. And that's achieved by having sufficient well spacing and a very large fracture system or reservoir with a lot of permeability, where we get a lot of contact area with the surrounding rock. I promised you I'll show only one slide with equations. You don't have to understand any of this, but you can, in terms of the details, but the concept is important. It turns out very, very simple models can be used to look at how we extract heat from rock. And if you just focus a little bit on this diagram, imagine that we had a single fracture for a moment and we're flowing fluid through it, and there are rocks on either side, and that rock could be arbitrarily large. And what we're interested in is what controls the rate of heat transfer from that rock mass, which is hot initially, to the fluid being pulled out of the ground or being circulated through this fracture system. And a couple of variables determine it. And it turns out that the area, the total surface area of that fracture is very important. And the thermal properties of the rock itself, which include the thermal conductivity and a few other variables. And then finally, how fast we're pushing the water through that system. So the mass flow, which we'll call m dot here, and the total surface area, which is this A term over here, really will determine performance. So if we can achieve sufficient areas of, say, 1 million square meters, we can get sufficient flows out of a two-well system that put us in a commercially viable sort of scale of about 50 kilograms per second of fluid going through a reservoir like that. Now, you asked the question, I'm going to come back to reality here. How has this had an impact on people? Well, this is a picture of Reykjavik, Iceland in the 1940s, when they were not using any geothermal, when they were importing all of their energy, and they were primarily using coal and oil to provide heating and surviving basically in the country. I don't have to convince anybody this is an air pollution disaster, which has been occurring in other countries as well, that rely on that kind of combustion-based things for all their heating. This is what Reykjavik looks like today. And they have been able to do it in a period of time which is still of the order of the kind of transformation times we should be talking about for the rest of the world. In 50 years, they took a country that was 100% dependent on imported oil and coal to a renewable energy supply based on geothermal and hydro. Virtually all of their heating comes from geothermal district heating. About 20% of the electricity from geothermal and the remainder from hydro. And they also have the ability to kind of bring things to scale. They're producing greener aluminum, if you will, by using renewable electricity for the electroprocessing of aluminum ore. And they're currently in the process of evolving their entire transport system to one that would be based on electricity and renewable fuels. They can do it. They're a small country. They're 1/1000th the size, if you will, of the United States. But they set the right kind of standard for the kind of performance we should be talking about because they fully have integrated it into their economy. So you can talk about geothermal heating and lighting that's actually used for greenhouses to grow their food. This is the interior of one of their power plants. You literally, this isn't one that's being built. This is one that's been operating for about 20 years. It's incredibly clean in there. There are no combustion-based residuals that come out of this. Again, picture of Reykjavik. And this, believe it or not, is a famous resort called the Blue Lagoon, which actually is living off the wastewater that comes out of this particular power plant, the Schwarzschild power plant. And they've discovered ways in which they can use this not only to have people pay to use the resort, but also some of the medicinal aspects of what's in the water. So in fact, they've fully integrated geothermal into their thinking, into this kind of clean energy economy. And I think that's what ultimately we're going to have to do. But of course, not every country has Iceland's geothermal resources. So we have to go back to this diagram for a minute and do a reality check. And so remember, we've talked about this earlier. This is Iceland down in the lower right-hand corner. And this is New York. And if you like, put Pennsylvania in there as well. We're in the upper left-hand corner. So we have some work ahead of us if we're going to kind of achieve the kind of transformation that Iceland's made. We're certainly not going to do geothermal electricity in the eastern part of the country like they do in Iceland, but we have other resources. The sun's not out half the year in Iceland. It's at the Arctic Circle. So we can take advantage of solar and wind and things like that. They're virtually not using any wind at all in Iceland because they don't need it because they have these other resources. So you've got to take advantage of the resources you have and do it in an integrated fashion. So we think that heating itself might be the best way to go. So if we talk about targeting now for just geothermal heating directly, you go back to this diagram and again, look more carefully at what's going on here. Let's see if we can get this to change quicker. You find out some pretty quick things. This is a first order sort of analysis. And down on the x-axis here, we have the gradients plotted. Low gradient here, 20 degrees C per kilometer, higher over here. And we're representing in these three different bars what it would cost to put in a system with a fairly low flow rate and what the levelized cost of electricity would be. And that's what we're plotting here. We're not looking at heat yet. We're just looking at electricity. And you can see pretty quickly that if we had to live with today's technology and low flow rates, there's no way we would ever produce electricity. In fact, even with improved drilling technology, it's still very expensive compared to what we have right now for our existing generation of electricity, even with solar or wind. But if we go to very high gradients, which would be true in the western part of the United States, you can see why there is attraction to produce geothermal electricity. That's not going to be the case in the east. So here we are back in the district heating environment, and if I can get this to change. So it leads you again to district heating. Now, why might this be important? Well, this is a graph of what we call the thermal spectrum of energy use in the US. We're plotting energy demand in these big units, exajoules, as a function of temperature, and it's the temperature range. So this is the amount of energy that's used over a given range of temperatures. And you recall that for the US, we have 100 exajoules total primary energy. So when you see a number like 14, that's 14% of the total US primary energy is used basically for water and space heating at temperatures that are close to a little bit above room temperature, of course, but not that much, in the 40 to 60 degrees centigrade range. And all of these red and yellow colors here could be viewed as targets for low temperature geothermal utilization. And we know how we provide this now. This comes, and there should be something that comes up here in a minute. Yeah, almost 20% of the US primary energy right now, 20% of that 100 exajoules, is used at temperatures at less than 100 degrees, and most of it comes from burning natural gas and oil. So we burn things at several thousand degrees, and then we degrade that temperature down and use it for heating hot water in homes, et cetera, and for some for cooking. So now the question would be, why would we care, right? Well, if you really want to decarbonize, you should, and you want to do this on a national scale, you should be looking at the whole country. So this particular plot here is a sort of heat diagram, shows how much of the primary energy consumption of these states is tied up in low temperature heat demand in the residential, commercial, manufacturing, and agricultural sectors. And I shouldn't have to convince most of us that the New England states, New York, the incredible northern tier here, there's a reason why Colorado is like that. We can get to that later, but it's not because they don't have heating there. It's the way in which they provide electricity. Is really one that has a big heating demand. And so if you really want to decarbonize, you're going to have to get us away from heating homes, heating buildings, heating commercial entities with combustion-based technology. So this led us to think more definitely about what might be possible in our own region. Cornell a while ago decided it wanted to decarbonize its whole campus, so it led us to look much more carefully at what we have in our own region here. And so this is, again, the old graph we showed earlier. This is a so-called heat flow graph that gives us an idea that where we have higher gradients, we also have higher heat flow. And this is that, again, that Appalachian Basin that I showed earlier. And we know we can reach these kind of temperatures, 80 to 140 degrees at, say, 10,000 to 15,000 feet, virtually anywhere in this region. And so how did we use the data that we had to kind of refine this a little bit? Well, it turns out there's a long history of oil and gas drilling, not only in Pennsylvania and West Virginia, but also New York State. And all of that data has been preserved in terms of bottom hole temperatures, logs that are associated with those wells, even core material and cuttings. So we have a lot of geologic information and geophysical information, which gives us a way to get an idea of how good the system is in terms of accessibility to a given temperature. And we can put this together in models, and we've used a kind of a techno-economic approach to kind of give us a first order estimate of how you come up with what it might cost for the levelized cost of energy. So this is one that deals with certain models of the reservoir itself, actual well drilling costs, the district heating models, the capital costs of those, if we're using that. other data, could be weather data and other things, and the gradient maps and heat flow maps that we've shown already, integrated into a system that we happen to call geofires. And this is just a depiction of what this data might look like. So these are drilling costs as a function of depth. This is a typical type of reservoir model that we might use to assess how a conceptual reservoir might perform, gradient maps, building heat demand data, capital costs for the power plant, et cetera, for the heat distribution system. It has a pretty sophisticated platform where we can put a lot of data into it. So it gives us high resolution information, albeit with an inherent set of assumptions, but you know what matters and you can do sensitivity analysis pretty quickly. And so it allowed us to create maps like this, where we could essentially come up with ways in which we could assess different regions in terms of their potential. So this looked at what we'll call a commercially mature case, knowing we could go in and produce these workable EGS systems, if you will, earth source heat systems, and we can deal with the costs for what they would cost and what the demand might be in that region. So the size of these bubbles represents what the demand is. And obviously down here in New York, it's huge. We're not going to build probably a lot of geothermal district heating plants there, but along this section, which is the New York Thruway, or down into Pennsylvania, there are many, many sites which might be attractive for sort of first level deployments of district heating systems. The colors of these bubbles represents what the cost might look like in terms of levelized cost for heat. These are in dollars per million BTUs. So as we go towards green, they become more and more attractive. Now this has inherent assumptions that I can get to later, but the idea is there's plenty of opportunity once you go and demonstrate this at a place that would be scalable, perhaps to many communities that could take advantage of it, assuming they're willing to put in a district heating system. So this is what I'm going to spend a few minutes telling you about what Cornell's doing, because we think this could be a demonstration that would lead to future development in our region. And it's structured around this idea. Many years ago, the then president, David Skorton of Cornell, signed an agreement that he was going to take the campus to a zero carbon future, zero net carbon future for all the energy systems, all the energy we expend on campus, not just for the buildings, but also for transportation and other things. Very, very challenging, aspirational sort of goal. And it evolved over time, but now it's back to 2035 to reach this condition. Of course, the students are big supporters of this, many of the faculty, but the realism is it's going to be hard to do in terms of the cost and the rapidity of deployment. But there have been things that have been done already, which are quite encouraging. So this is sort of a cartoon that shows a picture of the campus here. And you can see that we're also connected to using the lake, Cayuga Lake, for cooling the campus. This is sort of the analog to the district heating system. We actually, during the summer months, extract cold water from the deep section of the lake. This is a huge lake, by the way, 2.2 trillion gallons or so. So a small amount of water is taken out of this relative to the lake volume. We do heat exchange at the shore of the lake, and then bring that chilled water up to the campus and use it in a district cooling system, very analogous to the district heating system, to cool the campus buildings, dormitories, offices, and laboratories. We have a small-scale hydro plant in operation that's been in operation for quite a while. It's about a megawatt or so of base load power. The campus itself uses about 30 megawatts of electricity, so it's only a tiny portion of the total. The vast amount of electricity right now comes from this fairly efficient combined cycle heating and power plant that takes natural gas, generates electricity at close to 60%, and then uses the waste heat from that for heating the buildings, providing hot water for the campus. So we're going to have to obviously replace that if we go to a zero net carbon future. So the way of doing that is to combine solar PV with wind for providing electricity, combined with hydro. Some of it will be done on campus, some of it may be purchased in third-party agreements, but also the heating now would be tied to this earth source heat sort of concept over here. and biomass for peak heating. So we'll focus on the earth source heat and biomass for now, but I'll just give you a snapshot here of what Cornell's done. So we implemented lake source cooling about 20 years ago. We transitioned from coal to natural gas about 10 years ago. So that dropped the carbon footprint, obviously, significantly. But we have to go further if we're going to get to zero carbon. The Cornell's hydro plant was upgraded, fully operational at 1 megawatt. We've expanded our solar capacity in the last year or so up to about 20 megawatts peak capacity. Not so good in the winter, but certainly gives us a lot of solar electricity in the summer. And we're in the continuous negotiation with trying to deploy wind in sort of community wind at about the level that we need to kind of cover a good portion of the electricity as well. We're converting Cornell's, one of the concepts we're looking at is converting the ag and food waste that we have on campus. Cornell is a big agriculture college as well. And so we have a lot of cows, we have a lot of agriculture waste. We can use some of that to generate biogas. We think that might be an ideal source for peak heating. We only have about 20 days a year that we really need this peak heating for. On a really, really cold day, Cornell would go to maybe 80 or 90 megawatts thermal. Remember, 30 megawatts electric, 80 to 90 megawatts thermal. And for the base load, we're talking more like about 50 megawatts thermal base load heating. And that would be supplied by this earth source heat idea, having earth source heat for the base load district heating. So that's the concept. So Cornell has got a lot of ability to work on this. Obviously, they're committed to carbon neutrality. We know a lot about large-scale energy projects. They put in lake source cooling and made it work. We've done other large-scale energy projects. We've never done a geothermal project at this scale, but we have a lot of expertise in the facility staff and a lot of enthusiasm about doing this, which is not common on all college campuses. And there's a terrific amount of expertise in the geothermal area as well as in the earth sciences area among the faculty on the university. And it gives us an opportunity to do something at a university that isn't commonly done. We can actually produce something at scale, involve students and faculty with kind of a teaching laboratory that would be very useful for workforce development and show students that they can have an impact beyond working just at a bench scale or in a discovery mode in terms of the kind of traditional research that's been done. So we think it's, in many ways, it's an ideal location. We've got existing infrastructure. It takes away a lot of the capital investment that would have to be. We know we can do this on Cornell property, and we have a lot of drilling experience in the region to 2 to 4 kilometers, which are the depths we're talking about. So it makes sense to at least think about how could this go forward in a project. And we know we can reach temperatures at that level of, say, 2.5 to 4 kilometers, that greater than 60 degrees, less than 100 degrees, certainly usable in the district heating system. We need to develop, obviously, the first level of a 2-well system and circulate water through the rock mass to extract energy. We've got to be able to produce it at a high enough rate to justify that kind of financial investment. So we're talking about reservoir lifetimes of 20 years or so, and those flow rates of 30 to 50, numbers I've talked about before in this presentation. And we want to utilize it for baseload heating at about 50 megawatts. We know what the temperatures look like pretty well. This is a kind of a map of the geology here, the lithologic cross-section, if you will. We're looking at potentially 3 targets here at different horizons. One is in the crystalline basement rock at about 10,000 feet and a couple of others up in the sediments just above that at about 9,000 or 8,000 feet. And the temperatures in that depth range, let me get rid of this, are in the range of, somewhere around 80 to 100 degrees, depending on where we are, maybe 70 to 100. Plenty warm enough and hot enough to be able to be utilized in the district heating system. So we've got the resource there. We just have to make the reservoir work. And it will change in a second, I hope. There we go. So again, just to give you kind of an idea here for what the peak heating demand looks like. So the red picture here is where we would cut this off and sort of say the base load will cover all of that. So clearly in the summer, we don't have a big heating demand, but we have a long winter here, as you know, And these green peaks here show what that peak heating is. It actually only represents a small fraction of the total amount of heat that we're supplying to campus, maybe less than 3% or so of the total. So we still have to have the ability to do it. We can't freeze people out on those 20 cold days. So we're thinking about how we might tie together base load earth source heat with waste biomass. And there's one other feature of this that's kind of unique, is that we're not sure what temperatures we're going to get to. And the other aspect is we want to make sure we can utilize the reservoir itself in the most optimal fashion. And a district heating system has inherent limitations to it. You need to supply a certain temperature and it returns a certain temperature. That return temperature tends to be too high for what you'd like to do to re-inject it back into the reservoir. So we are utilizing a kind of a combination of thermal storage on the surface, integrating heat pumps, as I'll show you in a minute, and making a conversion from the campus, which is heated by low pressure steam now, over to lower temperature hot water. All of that will cut down on the peak amount, and it really makes it easier now for biomass to provide this sort of peak heating. And that's what's coming through in a graph like this. So we can knock a lot of these big peaks off by managing it with storage and some biomass on site. The steam to hot water connection brings this down from what we had originally, which was the current blue lines here, to what we would have with a more efficient lower temperature distribution system. So all of it helps us to think about this 50 megawatt base load heating, which we could just draw a horizontal line along here. You can see that more or less would take care of everything but those peaks. So it takes us back now to how we might utilize a biomass facility in somehow gasifying, if you will, either a combination of anaerobic digestion, thermochemical conversion, pyrolysis. We also do hydrothermal conversion. So there's ideas here that are being toyed with right now and analyzed as to whether they would make sense to bring to scale. And so we're thinking of how we could utilize things that are already here. Cornell has 600 dairy cows. They produce manure 24/7. They produce all of the milk and all the other products, dairy products we use on campus. But that waste essentially carries a lot of energy generation capacity to it, and it presents disposal problems right now for us. So using it in a way where we could get energy value out of it, use that for peak heating, seems to make sense. It would also help us reduce the environmental burden of this. On top of it, New York State has recently enacted a law that requires that food, if you generate more than 2 tons of food waste per week, whether you're Wegmans, a supermarket, or whether you're a campus or a given restaurant, you cannot put it in a landfill anymore. And you're going to have to do something with it. So it makes sense to have it processed in some way to convert a portion of it at least into usable fuels and to take advantage of that. So we have a kind of a number of concepts we're considering. This is just one depiction of this where we're using a kind of interesting idea where we use anaerobic digestion, which is used today to make biomass. That also produces carbon dioxide, but we then upgrade the carbon dioxide using renewable electricity through forming hydrogen by electrolysis, and then a biomethanation process, which allows us to more or less double the amount of natural gas. We would inject that back into the grid and use that as our storage capacity. So the infrastructure for the gas already exists, and our ability to generate it with the existing resources we have on campus are more than sufficient to take care of peak demand. So that's attractive. What it will cost and what the capital cost might be are not necessarily as simple. So this is a picture here of how we are, so advances in engineering utilizing centralized heat pumps and advances in subsurface engineering. I said a lot about subsurface engineering, but I haven't said a lot about heat pumps themselves. Let's take a quick look at this and we'll give you the concept because it's pretty important. So when we come out of the district heating system, we have relatively cooler fluid, but it's not down to the temperature that we'd like to re-inject it back into the reservoir. And we want to heat that up in a way where we get the maximum value out of it to return it to the district heating system. So we know this supply temperature and we know this return temperature. We also know the supply temperature that's going to be coming out of the geothermal reservoir. So if you can envision now using a series, and it looks like 3 of them, of these kind of centralized heat pumps, they will take a fraction of that heat out of here and convert some of it into increasing the temperature of this while we're decreasing the temperature that we're coming out of the ground with, so we can re-inject it at a lower temperature. So in simple concept, we always get the same temperature out, but now we get more value out of the circulation of the fluid through the reservoir because we're putting colder fluid down. So we would probably be injecting fluid at about 20 degrees centigrade and taking it out maybe at 80 degrees centigrade. If we didn't have this heat pump system the way it's shown here, we would be re-injecting it probably at 50 degrees centigrade rather than 20. So we're getting much more value. That has an enormous impact on the costs. Improves the potential targets, significantly improves the economics, enables active reservoir management. And this is kind of the bottom line of this. If we look at a couple of these formations, one is in the crystalline basement, the other is one of our sedimentary targets above that, about 2.3 kilometers depth for 3 different flow rates that we have between wells. These are the dollars per million BTUs. These numbers are very low. They're very low and very competitive. In fact, they're even less than what Cornell now charges the various colleges for heating their buildings. So it doesn't include the infrastructure costs, obviously, or paying off the power plant, things like that. But it's a very attractive number if we think about a transformation over to a district heating system based on geothermal. So if we didn't have the heat pumps, without thermal storage and biomass peaking, these numbers would be at 12 cents or more, 12 to 9 cents or more per million BTUs. So it has a big improvement there. And if we had a natural gas boiler at commercial rates for supplying the gas, we would be talking about $9.4 per million BTUs for a levelized cost of just the heat alone. So this is attractive and hopefully attractive to the university people who have to make financial decisions. And it's given us a big boost with securing funds for moving ahead with a project. So these are kind of the preliminary. I've got only a couple slides here. This is sort of the integrated sort of heat pump idea. Thermal storage, alternative peak heating, substantially improve the economics. They allow us to do operability. We were using similar technology that's been used in the Paris Basin for district heating there, using a different concept for supplying that hot water from an aquifer, but still the same idea of integrated heat pumps to get better value out of the overall system. Better building design, integration of low temperature cascading allows us to reduce temperatures and costs even further and continues along the reduction in greenhouse gases. And we've assumed reasonable productivity for the reservoirs, not something that's exceptional. So this is what's achieved now in commercial systems. And if we can prove that at the site we're at right now, we would have what we think would be competitive levelized cost for heat. Using peak heating using renewable natural gas generated from campus ag and food waste is potentially feasible, obviously needs a lot of further evaluation. So we have one last big step, which is to drill this first well. We were supposed to start this next month, but it's probably going to be postponed now, partly due to, let's call it the red tape of bureaucracies on both ends, both at Cornell and the DOE. So it'll be more likely early next year when we start to drill this first deep hole. It will go down to about 10,000 feet. It'll tell us a lot about what we have in the subsurface. So it does a lot of technical de-risking for us to lead us to designing this bigger system with multiple wells. It provides a kind of a laboratory as well for research that can be carried on campus. So it has that kind of educational and research connection back to this living laboratory concept. And it certainly helps us in mitigating long-term potential hazards or environmental impacts because it becomes a monitoring well for the future system that we'll have in place. So these, I think, are the kind of takeaways that I hope everyone gets out of this tonight. Earth source heat provides this sort of living laboratory research opportunity at scale. A systems approach has allowed us to integrate earth source heat being
Jeff,
Sorry,
we lost your audio
When did I lose it?
just 30 seconds ago.
Okay, so again, you can read the slides as quick as I can go over them, but these are kind of the simple takeaway messages, and there should be another one coming up here. Yeah, so we believe that success at Cornell would demonstrate this as an affordable, low carbon, renewable option. Remains to be seen if we can get to that stage. There are a lot of steps that are required. We think that this thing we call CUBO, the Cornell University Board, de-risks the project, opens up opportunities for research funding, whether it comes from the Department of Energy or from foundations or from other aspects of local or state entities, remains to be seen. But it's going to cost a lot to do it. We have committed now about $2 million of our own resources, more than that in the infrastructure changes that have occurred at Cornell. I'm not counting those. This is just associated with the project itself. The DOE has committed about $7.5 million for testing and drilling this first exploration well. But to really do it, to get to the point where we can walk away from this and say it's going to work, it's going to be another 20 million that will be needed to construct and extensively test a two-well production system. We have lots of partners in this, US DOE, NYSERDA, a number of companies, other universities are involved, particularly West Virginia University and companies. And I think this is a good place to end. And I believe we're there, yeah. So let's end with this, and I'll be happy to take on any questions you guys might have. Is that all right, Chuck?
Well, it was wonderful. Wonderful. Thank you. Thank you very much.
Okay, so Joe, you're going to manage this for me, I hope?
That's correct.
Okay, I can come back to however you want to do this. It's up to you.
You can leave the slide. You can leave the slides in case you want to come back to one for clarification.
Okay, all right, fair enough.
And
Yep.
we'll just do the Q&A with your takeaway messages up for now.
Okay, great.
So the first one, Joe, do you?
Yeah, I'll just kick it off just to get things flowing, if I may.
Sure.
Any idea how deep a typical well is in, say, Iceland for geothermal extraction
Sure,
versus
yeah,
a well needed for this project?
Right. So, yeah, so that's a really good question because it depends on what we're going to use it for, Joe. If we're going to use it for direct use, it could be very shallow in Iceland. Okay. In fact, the early deployment of geothermal in Reykjavik, downtown Reykjavik, they were drilling holes right in the town and using them. They were probably a few thousand feet deep, not 10,000 feet deep. But they are in the business of using their geothermal today in a cogeneration mode where they generate electricity at the high temperature end, and then they bring the heating back to the town. This picture of me here, we can go to, maybe I should show this if you can see me in this, right? The background of that picture is one of those Icelandic plants where they bring the fluid back to the town, back to the city of Reykjavik. It's about 35 to 40 kilometers away in well-insulated pipes. So the first part of the plant is generating electricity. The lower temperature heat that comes out of their flashing system that they use for this is directly converted into the heat that they bring back to the town itself. We're not doing that at Cornell. We would just do the direct use for the thermal energy. So that would look more like shallow wells. These wells would be 4 or 5, maybe as deep as 10,000 feet, probably more like 6,000 to 8,000 feet. But remember, Iceland is a hugely, it's a volcanic island, lots, very high gradients. So it's not a total fair comparison. Right.
Okay, thank you. One question, at 10,000 feet, is it possible to hit a natural gas? There goes my question. Is it possible to hit a natural gas reservoir? And if so, what happens then?
Right. Well, certainly not going to be possible in New York, okay, where we are, because we're in the crystalline basement. We enter into the crystalline basement at about 10,000 feet. The information that we have from other wells that have been drilled regionally is that there's not much gas in those lower regions, those lower sedimentary formations. It's well below the Marcellus, well below the Utica Shale, and things like that. So it would be unlikely to have a real bonanza of gas production. Okay, I'm not saying it wouldn't happen, but pretty unlikely. But once we're in the basement, now that would be very different as we go deep, as we go further south, because the shales dip further to the dip south, basically. So you'd be much deeper in Pennsylvania and even deeper in West Virginia. And again, that's why they discovered in West Virginia they had such high gradients, because they were drilling very deep gas wells and oil wells. We don't have to do that in New York, except there's a moratorium right now on drilling for shale gas, but there's still a lot of information about those upper level formations in terms of gas production.
Right.
Every region will be different, right, for sure, and has to be considered. Good question.
Is fracking technology envisioned for these projects?
Well, it depends on what we lump under the generic term fracking, right? Okay, if we're talking about high volume, high pressure injection with multiple completions as we have in a typical gas fracking operation now, no, it will not look like that at all. It would be much lower pressures, much lower volume, and lower rates of injection. And in some cases, would not probably involve much additional pressurization at all, depending on what natural fractures would be there. Our objective is to use the water, not necessarily to use the water as a means of creating surface area and then throwing it away. We're actually want to circulate that water for long periods of time. And this is something we have to learn about, but all the evidence that we've seen so far in geothermal development suggests that you can very carefully control the kind of behavior of these opening fractures by not necessarily going to very high pressure, certainly not the rates that they would for we're not trying to break the rock down. We're trying to reopen natural features that are in the rock already. But it's a great question. And water is our friend, not our enemy. Remember, water, we need the water, right?
Okay, this question is a little long, but it's the money involved in this technology seems excessive. Is there not much more to gain by making the existing equipment more efficient? I see a lot of, cases.
Okay, so this is a good question, because it looks like it's excessive, but it's really not excessive if you think about what we're doing. We think with 3 well pairs, we can produce that 50 megawatts of thermal energy that we need for the whole campus. And so the first well pair might be 20 million, maybe it's a little less for the other 2, but all the infrastructure is there to start with. So that would be the big expense if you had to come in and retrofit infrastructure. And I think someone brought this up earlier before we got started, that ultimately we have to decide how much it's going to cost to get to low carbon. There are no carbon credits worked into any of the economics we've done so far. That would have to change, obviously, if we were going to put in district heating infrastructure. But these costs are not excessive. You look at those levelized costs for heat, that is really low. So I'm not discouraged at all that we could, in an early deployment, could meet that kind of performance economically. You need a lot of capital to do it, but I don't know whether you've looked at the capital required to build a power plant, but when Cornell built its cogen plant, it was significant. And we're paying that off over 25 years. And that's one of the reasons why it costs so much to deliver heat and electricity to campus. It's not the cost of gas. It's the cost of paying off that investment. So this has essentially a zero fuel cost, but it's all in investment to start with. But it seems to me it's pretty competitive. One feature we need to think about the efficiency question is, when we take 100 units of heat out of the ground, out of say 80 degrees centigrade water, put it in any units you want, joules, BTUs or so, we take 100 out of the ground, we utilize about 90% of that thermal energy in the district heating system. So we get a lot of value out of that 100 that we're pulling out. If I were making electricity with that, I would be throwing away 90% of that. So the same investment for the subsurface system, it's identical for the subsurface system, but we get 8 to 9 times the value in terms of what we're delivering. I don't know what you guys pay for natural gas at your house, but it's pretty expensive in New York because you have to pay a delivered price. Same for electricity in New York. And these prices, if you could achieve this, would be pretty competitive. But we need district heating. You know, we need to have the infrastructure for it. It's a great question. There's always more to it than you can present in 45 minutes or so.
Of course.
Right.
Does the $20 million build a complete functional system at Cornell? And if not, what is the estimate?
Right. It completes a functional system for about a third the campus. And we're transforming the campus sort of section by section to low temperature heating. So the timing for this would be perfect for a section of the campus that's already on hot water heat right now. And so the next level would be more of the campus will be done in a few more years. So we'd add a few more wells. We'll learn a lot about the performance of this system and help de-risk it even further by operating a 2-well system for a while. But it still will take additional investment. But eventually we have to figure out what to do with the power plant. Maybe we'll sell it to you guys, you know, and because it's still pretty efficient. But if we're going to go to zero carbon, we can't be using natural gas in it. So it's a kind of a, you know, you've got this big investment. Someone could buy it and run it and produce that power back to our local utility in some you know, very aspirational world. Maybe we could do it on renewable gas, but that's a lot of renewable gas. We have almost 650,000 cows in New York. If we could somehow convert all the manure, we could probably make, you know, a lot more renewable natural gas, but it's not all going to come down to run the Cornell plant. I can tell you that for sure. So there is always this opportunity of what's the best way to do it in this kind of financing end of it. And I'm not an economics expert, but I know that's one of the reasons why we have to have a lot of partners. We have to have people who want to make a business out of this eventually. The company NG here is the company that manages the Paris Basin project right now. And they're very interested in trying to do the similar kind of thing in the US. They run power plants in the US as well. So they would be a logical company who could deploy this on a much bigger scale in Pennsylvania, New York, and the Northern Tier. So they're very interested in being a partner at an early stage of this. There are a number of other smaller operations around the country that do district heating, but they're primarily all out in the West. And they too are interested. For instance,
any concerns from the New York regulators with the drilling and the project overall?
Well, for the exploration well, I would say no. Okay. When we get to the point of putting in a 2-well circulation system, it's a new ball game because they have no experience with this, right? So it's not a gas well, it's not an oil well, it's not a typical mining operation. So they'll have to take some precedent on what's been done in other parts of the country. So I expect that process will require some time. But remember, we didn't set the goal that Governor Cuomo did. He did, okay? And the state has bought into it. So if they want to decarbonize the whole state, they're going to have to get serious about this. They cannot do it just with heat pumps, either air source or geothermal heat pumps. It will not handle the scale that they needed, particularly in the winter, because they're going to require a lot more electricity in the winter, and they don't have it. They certainly don't have it from solar. You know what it's like in the winter here, right?
For sure.
And we don't have the wind capacity in New York State that we would need to make up that difference yet. So I think there's opportunities for a buy-in of the regulators to say, yeah, maybe we're going to have to take a different look at this and get more efficient at the way in which we license geothermal plants that do heating. But they have no experience with this yet. But the exploration well is different. It's, you know, this is a scientific thing. We're not going to use that for production yet, for sure.
And just a comment that it seems like this type of technology would be applicable in the states of Hawaii and Alaska as well.
Well, certainly, well, Hawaii, I'm not sure they need much district heating, but maybe we could do district cooling with absorption air conditioning and things. There are issues in Hawaii because a lot of the Hawaiian islands are in protected lands. They're in national parks and protected areas, and we're certainly not going to go into those. And frankly, Hawaii has so many other resources, you know, huge solar resource, better wind resources, and they don't have the heating load. So to me, they could do this in a different way in Hawaii. Alaska's a different story. Alaska has other issues, you know, its remoteness is one. Where there really high-grade geothermal resources are, people don't necessarily live. But we're certainly looking and working with our friends in Alaska right now on opportunities there too, at least from a conceptual point of view. But I think if you look across the northern tier, states like Montana, Illinois, Michigan, Wisconsin, all could reach temperatures which would be usable for heating, and they have huge loads there. All the New England states, certainly true, and Pennsylvania and New York as well.
Thank you. Will the water become contaminated with dissolved minerals and therefore require cleaning and add expense?
Another great question, right? We don't know yet. Okay, each system will be a little different. Experience says, one, we're going to reuse the water. So we're essentially all we're doing is removing a little bit of thermal energy and putting it right back down into the system. So presumably it would have a modest effect. It's not like a real high temperature geothermal system where you're injecting very cold water in an extremely hot environment. We'd be going in at 20 degrees and only heating it up to 80, not going in at 20 and heating it up to 200 or 300 centigrade. So the rates of chemistry interaction between rock and water would be very different in that lower temperature regime. It doesn't say we might not encounter problems, but I think they would be manageable. And we won't know until we have a two-well circulating system for sure. Every geothermal system, you know, if we stopped and looked at every possible thing that would fail, we would ask the question, why do we have so much geothermal around the world? We have countries that, you know, I would regard as pretty undeveloped: Kenya, Ethiopia, a lot of Central American countries, Nicaragua, certainly many countries in the Philippines and in Indonesia. They have huge geothermal resources that they're utilizing now. So they've managed to do it in a way. Of course, Iceland's a classic example, but that suggests that they are engineered in a way where they can live with what the chemistry is, can live with what the seismicity might be, can live with the water that they have available and make up whatever water they need. So it's not like we don't have a lot of experience. I might point out one thing, since you may be curious about this. Where was the first geothermal district heating plant built? Anybody want to take a guess at that? In the world. Where do you think it's built in the world? Anybody know? I'll tell you what, I'll give you $1 or so if you can get it right. Right. Okay. What if I told you it was in the United States? Would that help anywhere? You know, we always get credit for inventing things and then someone else develops it. Well, it turns out about a few decades after the Civil War, we opened up our first geothermal district heating plant in Boise, Idaho. And it's absolutely still operating today. It's part of the Boise City district heating system. It heated all the municipal buildings. It's heating part of the Boise State campus now and other buildings in the community. And so we invented it in a sense, in quotes, if you will, and then it got deployed in a massive way in countries like Iceland, some in France as well. The Chinese now have taken over, and they have deployed more geothermal district heating than any other country, not because of decarbonization, by the way, just because they've got to replace that horrible coal-fired heating they have in all these cities that is making it unlivable for them. So the whole idea was to get rid of the local pollution by going to geothermal district heating. The advantage that the Chinese had, they have all the infrastructure in place. They have the district heating infrastructure. And so all they have to do is say, we're going to do it. So they started drilling wells and put it in, and it's working pretty well. So they're largest country now producing geothermal district heating. And they did it in about 10 years. It might take us a little longer than that, but we got started early in this game. We just got out of the business because we had so many other resources.
If another question about fracking, if a gas fracking well becomes depleted for gas withdrawal, then can it be reused for hot water?
Well, that's another good point. Providing that the well diameter is drilled in such a way that it can handle the flows we need. A geothermal well requires a pretty big flow of water, thousands of gallons a minute or so in terms of flow. When you do 50 kilograms a second and convert it to gallons a minute, you'll find out that's a big number. And so you need a bigger diameter so you don't have such a big loss of pressure in the well, both the injection well and the production well. And a lot of gas and oil wells aren't drilled to that larger diameter. So a typical geothermal well diameter would be larger. So it isn't always the case where you could use it. There are examples, obviously, if you're producing a lot of water out of an existing oil or gas system, why not use the hot water that's coming out? And there's a big effort of so-called co-produced oil and gas and hot water to utilize the hot water before they re-inject it. That's a little different than turning it into a big district heating operation. They're just using it locally at that site. And that's going on primarily in Texas right now and other locations where they have a lot of existing oil and gas production that's pretty deep, where the co-produced water is hot that comes out of the ground. Good question, though.
We have someone who's working on a fuel conversion project from about 1.2 million gallons of fuel oil per year to natural gas. And they want to know if you can comment on technology implementation timelines, because they'd like to recommend this be paused, the project that they're working on be paused, so that newer low carbon heat sources can be used rather than lock in a 20+ year agreement for natural gas investment.
Right. Well, I mean, obviously when you have this sort of overriding goal of decarbonizing, you look at a lot of options. So the ones we've been looking at with respect to renewable gas use wastes, obviously. So the wastes are there, so we don't have to worry about supplying those. But the technology, although it's there in pieces, it's costly, right? You still have to put in the capital investment that you need. This biomethanation process I mentioned is available at a maybe 1 or 2 megawatt scale now. There's a company that was started in Holland that's developing this, and they have a U.S. entity now that's working on it. It's called Electrokia. So they know they can do it, but you have to buy electrolyzers. You have to be ready to do this. You got to build the reactors. So you really have to be committed to a long-term contract where the price of renewable natural gas would far exceed the current price for natural gas. In other words, you're essentially buying into the low carbon future. And I don't think we're totally ready for that as a country yet. Although the state of California is doing it now, I don't think that's as widespread as it would need to be. But it's a great question. It's not just the cost of the fuel supply itself, or the feedstock, if you will. It's also the cost that you have to invest in all the other capital to make it work. And I think some incentives would have to be there, either carbon prices, offsets, as we have we put into a lot of solar and wind development, and they're not there yet, but they could be. And I think that's what people are looking at right now, whether
they should be.
They should be, right, Chuck. We're not the policymakers, right? Right's your congressman, right? And I don't think there's any doubt that we need to do this stuff. I just hope it occurs in my lifetime. I look at my young students in the class every day and I say, look at what we're leaving these kids and their children. We've got to be better at this. We've just got to be more, the sense of urgency has to come quickly, I think.
10 years ago, I said that natural gas was a bridge and that it was a, valuable investment.
Sure.
I don't tell them that anymore at all.
It is, it's a real issue, I think, for everybody. the transportation side is particularly challenging too. I hope you guys have some talks on that because, you know, I'm a big fan of where they're going now with electrification. But when you start to look at what the electric loads might be, if we have a couple of hundred vehicles that require renewable electricity, it's going to be a big shift to our current infrastructure for electricity, and that has to be thought through carefully before we totally give up on gasoline, right? And so it's going to be challenging, but you know, in a sense, it's an opportunity. But I wish we had more sense of urgency right now, on both state, federal, local level. I wish people would make the connection between climate change more directly and sustainability more directly. And they're not doing that yet. I mean, we got a big diversion now with COVID for sure, but I wonder what will happen as we go forward here. But we might not have a Congress that has a budget that's operational. The country may not be operating in a few days, right? Which is also embarrassing, right?
I have another question. What is the minimum size of a community that might reasonably use this technology?
Great question.
How about a retirement community with 800 residents, 2 swimming pools, laundry, etc.?
I think it could work for that size. We cut off our lower boundary on that study I showed you with all those balloon figures that we had was about 2,000 dwellings, okay? But it on some scale, depending on what that well cost gets to, okay, you could go to somewhat smaller communities. I think if you get too small, though, it makes more sense to think about geothermal heat pumps and district energy that way, where you efficiently run it with that system, and maybe you use some other creativity in available resources that are nearby. But it's a real tricky thing when you get into real tiny communities. Now, Iceland has been able to do it. I don't know whether you visited Iceland, but you know, there's only 300,000 people in the whole country, and 200,000 of them live in Reykjavik, basically. And then you go to some of these communities, and there's 4 or 5 houses. They've managed to put in piping, and they bring the fluid to them and give it to them. So they have provided the kind of infrastructure. It's sort of like power now, right? You live in a very rural area, they bring an electric power line to you. Well, in Iceland, they bring a pipe full of hot water as well. And we're not ready for that yet, but we may have to be. And that would cover that minimum community size very nicely. But we're certainly not there yet. And I hope we do get there someday, but anything would be better than what we're doing now, right? Which is burning natural gas and heating all these homes.
But again, this is screaming distributed energy resources. It's
right. And it suggests
for,
go ahead, Chuck.
I'm just saying it's prime for combining renewable energy sources with a microgrid and a distribution system that's localized.
Right. And I know we haven't talked about a lot about other alternatives for low carbon. I figured there'd be at least one question for nuclear, but we have to reconsider that too, because the idea of what's happened in New York now in the past few months is really crazy in a way. They've just shut down Indian Point. They took over 2,000 megawatts of baseload decarbonized energy offline. And they think they're going to make it up. Well, they're only making it up with natural gas. They're certainly not making it up with solar or wind. And so they're making their challenge harder by essentially, taking the existing capacity we have for low carbon offline. And I think we're going to need everything. I think every single thing we're going to need in the low carbon future. So we shouldn't totally discount the nuclear side of it either. I know that, maybe there's bad feelings about 3 Mile Island and things like that. But compared to some of the things that happened in coal mines and natural gas explosions, it's kind of not that risky. It's got other problems for sure, but not risky in terms of safety, I don't think anymore.
Jeff, can you comment on the seismic activity and the possibility of earthquakes?
Sure. So for the exploration well, I don't think anybody's worried. But when we start to circulate water through a system, we would have to very carefully ensure to the public and to ourselves that we understood what was going on downhole. So that monitoring ability, both with high resolution seismometers, would be done as part of a routine. Any geothermal development in the country is done that way. We would want to make sure we understood where fluid was going, so the mass balance on fluid being circulated, so we're not having massive fluid losses. And we'd want to carefully monitor those pressures, so injection pressures, recovery pressures. One of the ways, so there is going to be some potential for risk, but we believe that it's very manageable, particularly with the way in which we produce a geothermal system. Many geothermal systems in operation today are incredibly seismically active regions. In fact, there's one just very closely located in Iceland right now, an erupting volcano with lots of seismic activity, and the power plants are still running. And I think we've seen a lot of, the ability to manage high seismic risk areas with geothermal systems. So I think in a low seismic risk area, you've got to be very careful to ensure to the public that you're not increasing the risk by what you're doing. But we think we can do that by proper management and proper control. After all, we have control of the hydraulic system because we're connected to it at both ends. So it's not the same as what's caused some of the seismicity risks in shale gas, where you're literally pumping water into the ground. With no circulation, you're getting rid of the wastewater that way. And that's what's happened in Oklahoma for sure. That would not be, that's not even close to what we do in a geothermal system. So it's a great question, and there's a lot of interest in understanding the seismicity. We actually need some seismicity to understand the system. We need to be able to map it in three-dimensional space and in time. So microseismicity is our friend. Large-scale seismicity is not our friend, but we don't believe we're going to have to deal with that. Does that cover that? I mean, it's a tough area. You're muted too, Chuck.
Yeah, you got a question from our president, Joe.
Go ahead.
Yes. What happened to the capacity of the facility that's located north of San Francisco?
Oh, another great question. Okay, so we have a habit in the United States and maybe other countries that when we have a good resource, we overproduce it and we don't manage it well. Gold mines are that way, right? And others. So what happened at the geysers field is that it's a steam system. So it's a natural steam dome. And they actually produced too much steam out without enough recharge because they were losing some of the water through evaporative cooling. They were using evaporative cooling for the cooling side of their thermal system to convert electricity. So instead of injecting 100% of the water, they were maybe only injecting 50% or 60% of the water. The rest was evaporated. So eventually the pressure dropped and the production level dropped. So at some point a while ago, people said, oh, we're going to just not be able to produce the system. Well, American ingenuity comes up with another idea. So the city of Santa Rosa, which is not too far away, had a problem with disposal of its sewage water treatment. And so the secondary and tertiary treated water was then, a pipeline was built and they re-injected it into the geothermal system. Now remember, this is hot too, so we don't have to worry about pathogens or anything like that coming back out. And it actually sustained the production. And they were actually able to get to a kind of a sustainable steady state production, less than they had for the peak, but still very sustainable now. So they could use the same power plants, but they're partly derated. They aren't producing quite as much power, but they're there, right? And so I think it was a lesson learned. That will not be the case in the way we're going to operate our own system because it's total rejection. We're not evaporating any of the water. It's low temperature for one thing. We're going to manage how much water goes in and how much comes out. But it's still an issue. We want to make sure that occurs because water loss could be a big issue, more for seismicity than production loss in this case. Good question, Joe.
And I think that's it for questions that I see. If there's anybody else that has a question.
Anybody from the audience?
Yeah, we're happy to take things on heat pumps too, if people have any there. I have a geothermal heat pump system in my house, guys, so I can tell you how well it does, and I'm very happy with it, but it requires an enormous amount of electricity in the wintertime, right?
What's
And
a
I'm providing
COP?
that, I'm providing that right now with photovoltaics, but not directly. I'm storing it on the grid and getting it back in the winter.
What's the difference in the COP between the summer and the winter?
Okay, the COP is actually pretty good even in the winter because the temperature is more or less uniform. It goes down a few degrees, but the demand is higher. That's the problem. I just have to produce more heat for the house. So the COP is still good, but remember the COP is only the amount of heating that I get relative to the amount of electricity. The amount of heating is what's going up. And I still get the relative fraction, but it's much more net electricity. But
Okay.
the COP probably for my system average for the whole year is somewhere between 4 and 5. It's really efficient right now during this time because there's no, we don't really have to turn on the compressor. We just take whatever residual heat is left in the ground. I've got about 2,000 feet of coiled tubing in the ground here in 4 deep channels, 200 feet long each. And so it's pretty efficient, but it's more expensive obviously than an air source system. But the COP in an air source system in the dead of the winter is terrible, as you know.
Yeah. There's one more question here, Jeff, and then we're going to let you go. Joe, you want to ask this question?
Sure. Does geothermal energy have the potential to replace, say, a 500 megawatt gas or coal-fired power plant, or should we think of these as potentially smaller energy sources?
Well, I think if we're talking about 500 megawatt electric power plant, I think that would be pretty wishful future for this part of the country because we'd have to drill very deep to get to higher temperatures, and that would carry its own economic risks as well. But if we're talking about heating directly, and you wanted a 500 megawatt thermal heating plant, that would cover a pretty big city, of course. You could certainly envision that, but it probably would not be in one plant. Because of the logistics of this, you'd probably have modular systems, several, maybe 5 or 6 well pairs for each one, and connect into the district heating in different locations. That's certainly the way Iceland does it. And I think a large city would find that more usable. Then you could spread your distribution infrastructure out a little bit so you're not having to deliver large amounts of fluid across the whole city. You could be delivering smaller amounts where you needed it. So, but the fact that Iceland's able to deliver that fluid by I think the longest one they have is like something like 75 or 80 kilometers. That's unbelievable. If you imagine putting in a pipeline like that, and they managed to do it with very little loss in temperature, and they figured out, in a simple way how to build these things. They put it in a country that has a huge amount of seismicity, so they have to make them all earthquake proof. So if we could do this on a larger scale, but I think the economics would suggest a more distributed system, not big centralized system. And that's better anyways, right? For a lot of reasons. It's more resilient to difficulties if you have, power failures or whatever, or it's more friendly to the local people. It's like having a local, Cornell is a little distributed system, right? 30 megawatts. 50 megawatts serves 20,000, well, roughly, if you count everybody, about 30,000 of us. So Cornell itself is 1/10 the size of the whole country of Iceland. Think of it that way if you want. And we're, a huge step forward if we could make this work for other places. I think it would be ideal for, places like Penn State and other locations like that for sure. Army bases where you've already got, embedded infrastructure there and you want reliable low carbon energy. Hospital complexes, large school complexes. I think a lot of the state universities in New York could utilize this too. So it's a
Wonderful.
step forward.
Wonderful. Jeff, thank you Dr. Tester, thank you so much for sharing your time and your expertise with us tonight. We told you we'd give you a hard stop at 8:30. We've gone past 8:30.
Okay, well, thank you for the chance to do this, and
Time to say goodbye.
I hope someday we can come back and actually show you this operating, but if you get a chance to come and visit us during the time this is being drilled, be sure to try to do that. It's a short drive from Pennsylvania for sure.
And we will definitely have you come back and give us the update on this in a couple of years.
Okay, and if not me, there's plenty of others that would be good at this too, from Cornell too.
All right.
Thank you so much.
Yeah,
Yes,
thank you guys.
Thank you.